Now, then how about for the current, right? How do we find the currents? A lot of derivation, maybe you learn in other class, such as E221, right? But it is very simple after all. We just remember this one, ID equal to IS times VD divided by phi t minus 1. Do you know what is phi t? Here, although you might not have the same symbol, but based on this equation, what is phi t? Do you remember?
Built-in voltage?
Say again.
Is it the built-in voltage?
I cannot hear the last one. Voltage, what voltage?
Built-in potential voltage.
Not the built-in one.
So it should be 26 millivolt.
Yes, it's the thermal voltage.
Oh,
K
okay.
P over Q.
Q, okay.
Yeah, it's just standard, but very good. Very good. Yeah, it's not related to built-in. The built-in will go to the IS, I mean relation, but very good, right? So you see that it is not a constant. It depends on temperature, right? So I already drawn the picture to you earlier. You see this one? This is linear scale, right? Let me emphasize, this is linear, right? You have to be very familiar with all the scale now. When plot the idea as linear, when it is forward bias, suddenly go up like crazy. Okay, if you plot in log scale, actually it's just a straight line. But you see, this is essentially zero because this is trillions of time lower current at here, right? 11 orders of magnitude. So it is very correct to say that this is zero. Okay, we can do a little bit of more approximation. If your VD means, what is VD? VD is this one, plus minus VD. The voltage across your diode, that is the VD. Okay, if the VD is much larger than phi t, then of course, exponential of VD minus divided by phi t is much larger than 1, right? When this is large. So your ID actually is just IS e to the power VD minus phi t divided by phi t. Right? And that's why it's just a straight line. If I take the log scale, log ID equals to log IS plus VD divided by phi t. Yeah, that's it, right? So it's linear. And the slope is 1 over phi t. And this is so-called 60 millivolt per decade, but I won't go into the details. But basically here, just to tell you, we need to have a deeper understanding on diode. Or if you put in the log scale, it's just a straight line. Do not think that this is just on and then off, off and then on. Okay? Any questions? Okay, with that, oh, what happened? Okay, I accidentally put one more slide. This one you can ignore. Now, how do we model it, right? How do we model the diode? Right, we can solve the equation. Of course, you can solve the equation, but it becomes a very complicated. For example, if I have a circuit like this, a very simple circuit, right? If I call this VD, right? This is R. Then to solve this circuit, I need to do KCL V in equal to IR plus VD. And then I also know I equals to IS e to the power VD divided by phi t minus 1. Then I need to solve it iteratively, right? I need to solve it. There's no open form or closed form solution, right? But as an engineer, sometimes we do some approximation. I think you learned that in maybe undergrad also, because now we say that this one goes up abruptly. So let me just call this one to have a on current called VD on voltage, which is VD on. When it is larger than VD on, you have a drop of VD on. When it's less than that, it is just 0. Okay, so then with this, then we can solve it as, we assume it is forward bias. We know V in equals to IR plus VD on, right? This, for example, it is given maybe 0.8 volt. Okay, and let's say this is 1.8 volt. Then what happened? Then you know that, and if R equals to 1K ohm, then I equal to V in minus VD on divided by R, which is 1.8 minus 0.8 divided by 1K, which is 1 milliampere. Right. This is an approximation, but you will be pretty close to the real result. Okay, so this is the model we will use. I mean, not we will use, sometimes we use. Okay, questions? Is that clear? So this is the DC model, right? How about for capacitance? Now, this is the reason I spent so much time to talk to you about the depletion width, right? What is the capacitance? Can someone tell me? Remember, capacitance is just C equal Q over V, right? It's just asking. In reality, it's actually dQ dV. It's asking how much dQ charge, right? I need to put to increase dV. You have a two-terminal device. If I need to, for example, if I need to put, for example, for this device, it was 0 volt here, 1 volt here, now become 1.1 volt. This is still 0 volt, right? So delta V is 0.1 volt. In order to bring it to 1.1 volt, if I need to put, let's say, 1 coulomb of charge, then the capacitance is just equal to 1 divided by 0.1, which is 10 farad. This is a very big capacitance, but just an example. Is this okay? That's the meaning of capacitance, right? And I'm sure some of you don't have this concept very well, so that's why I want to mention. Right? We know very complicated equation, but sometimes we forgot the most basic thing, and that is going to guide us on understand why something is defined in a certain way. Right, so this is capacitance. Any questions? Then why there's a capacitance for the diode? Remember that we have a depletion width. Right? To change the diode voltage, we already know that when you change diode voltage, XD will change, correct? We just discussed it. You increase the reverse bias, the XD increase. You decrease the reverse bias, XD decrease. When you do this, what does it mean? I actually change. I need to add or remove charge from the depletion region. Sorry, my writing is really bad because I hurt my hand and also not writing on the screen. If you cannot see, let me know. Is this clear to you? Right? I need to increase and decrease the depletion width. So I need to, it means that I need to add or remove charge. So there is a dQ in this process. And that's why I have a capacitance equal to dQ dV. And this V is VD, the diode region. And this Q is the depletion charge. I mean, the VD is the diode voltage and Q is the depletion charge. Okay, but we are not going to prove the exact equation you are given here and you use in your homework. A pretty complicated equation, but it should be straightforward to you. It is plotted here. And more reverse bias, we have smaller capacitance. Can someone explain to me why at higher reverse bias, the capacitance is smaller?
So the volume of the depletion layer decreases, so the capacitance also decreases.
So you're almost there. For larger okay, so for, right, so maybe now it becomes messy. Let's call this 1, this 2, right? And then I have another 3. Now you tell me, for large reverse bias, XD is large or small?
It's larger, right?
It's
Large.
larger, yeah, it's larger.
So when it is large, capacitance has another definition, epsilon divided by XD, right? Because you are adding the charge across this. This one I forgot to mention. This is basically just a depleted layer is not conductive. You add the charge to the boundary to make it wider and smaller, right? So now capacitance is large or small when you have a large XD?
Small.
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 Yeah. So that's why when you go to reverse bias, the capacitance goes down. When you go to forward bias, the capacitance goes up. So you need to be careful when you bias your device, right? Sometimes think about this capacitance. Capacitance is going to affect your delay. Okay. And this is the equation, right? We are not going to prove it. Take it for granted. It will fit this line very well. CJ0 is what? This is just the C at VD equals 0, just the equilibrium capacitance. So at 0 bias, we already say that you have a certain depletion width, right? That is the capacitance. Okay. And there are 2 types of junction. The M can be 0.5 or 0.33, right? So what is abrupt junction? Abrupt junction means that in the PN diode, you suddenly change from P to N, right? So maybe this is 1E18 and this becomes negative 1E18. This is N type and this P type. Very abrupt. Okay, this is abrupt. And you can also have other, and one of them is so-called linear. It just goes down linearly. Okay, this is still 1E18. This is 1E18. This is again P. This is N. And this is linear. So depend on the grading. This is what we call grading, right? From the P to N, you use different number. Okay. Right, so in this class, right, we will only use those capacitance that is related to the normal operation. Okay, so what number will we use? Usually it has to be reverse bias because you don't want to forward bias a PN junction. Okay. Any questions so far? This is a little bit messy, but I actually try to remind you some of the fundamental, right? If you don't understand anything, you still can just use this equation for easily. Right? But I think that will help your interview a little bit and also really understand why I'm using this. Right? So after all, the last thing to take home is that this is how you calculate the junction capacitance. Right? You have both forward and reverse bias junction capacitance. And reverse bias is smaller. Okay. Then how do I find out the effective capacitance? Because in digital circuit, right? The reason I want to find the capacitance is to find the delay. So I want to find the effective capacitance, right? We actually want effective capacitance, correct? But what is effective capacitance, right? For example, what is the effective capacitance when I switch from 0 volt to -2 volt or VDD, right? That is what happened to your junction in the MOSFET. So how do we do that? Then we just use the equation. We know C equal dQ dV. Okay, so as a result, the delta Q is just equal to C dV. So the total charge is just equal, you do the integration from V1 to V2, right? Okay, so that's how we find the total charge, right? And then the effective capacitance is just equal to, let me call it total, Q total divided by V2 minus V1. Okay, so for example, this is V1 and this is V2. Then this part is actually Q total. Okay, so what we care about is the effective capacitance. I will find out the area under this part divided by V2 minus V1. Then this will be the effective capacitance. And then I use it to calculate the delay. That is the idea. Because I'm not simulator. If you're doing H-spice simulation, yeah, it will just calculate the correct delay for you. But as an analytical equation, I want to know, let's say I switch from V1 to V2. This is the change of the voltage. I want to find what is the total charge. I just do this and then get the effective capacitance. Then I use it for other delay calculation. For example, 0.69 RC. Okay. So I will stop here because time's up. Maybe I mentioned this a little bit more, right? So sorry, let me finish this one, right? So how do you calculate that is I just told you, right? And this is the final equation that you will get. So what we are going to do is that you will get something called K effective time the capacitance and zero bias. And they already proved this. This is the total, the final result. This is like the V1, like V high, and then V low. Okay, it's just an equation. We are not going to prove, but you know all of this term already. Okay, yeah, I will stop here. Any questions?